vapor pressure of solutions of solids in liquids. We have discussed about liquid solute and liquid solvent based solutions. Now we have solids in liquids solutions. Vapor pressure is directly related to the number of liquid particles available on surface for evaporation. But in case we have solids in solution which are non-volatile, the vapor pressure because of them will be zero. So this is in a pure solute vapor pressure. As we saw in the Raoult'S law, total pressure of the solution surface will be equivalent to vapor pressure of pure solute and vapor pressure mole fraction of solvent. We subtract vapor pressure of solvent minus solute in its pure state. As we know, for solids, vapor pressure of pure solute will be zero. So we substitute zero here. Here it's zero. This is the vapor pressure of solvent. So total vapor pressure above the solution surface will be equal to mole fraction of solvent into pure vapor pressure of solvent, which is volatile. And that is our equation for non-volatile solutes. Here we are having a P0 vapor pressure of pure solvent. P is the vapor pressure of solvent in solution. Now we want to study the lowering of vapor pressure. We know in case of a non-volatile solute which is solid, there will be a suppression in vapor pressure because of the presence of these solutes. That change in or lowering of vapor pressure will be vapor pressure of pure solvent minus vapor pressure of solution, which is P. Here, the relative lowering in vapor pressure is defined as ratio of lowering of vapor pressure to the vapor pressure of pure solvent. That's what is called relative lowering of vapor pressure. Here we know Xa plus Xb, which are mole fraction of solute and solvent respectively, their summation will be equal to 1. So mole fraction of solvent will be 1 minus mole fraction of solute. Now we can substitute that in the solid and liquid solutions Raoult's law equation. That will be, since solute don't have any vapor pressure for solids, total vapor pressure will be equal to the vapors of solvent, which is that we saw the modified Raoult's law, Pb, which is nothing but vapor pressure of solvents, partial vapor pressure of solvent. This is a partial vapor pressure of solvent. Modified Raoult's law, we know here it was a earlier Pt, which is total vapor pressure of solution, but we know in case of non-volatile solute, we having a vapor pressure of solvent only, so Pt can be replaced with Pb as per this equation, and this is a mole fraction of solvent Xb. Subtracting both sides from 1, what we'll get is, this is a Pb by Pb naught, and 1 minus Xb, which is equivalent to Xa, as we know, mole fraction of solute. Now, rearranging the equation, what we'll get? Pb naught minus Pb divided by Pb naught. This we know is a lowering of vapor pressure divided by pure solvent vapor pressure, which is nothing but relative lowering of vapor pressure. So relative lowering of vapor pressure is equal to mole fraction of our solute. That's what we say. This is the equation for relative lowering of vapor pressure. Relative lowering of vapor pressure will be proportional to the mole fraction of solute. Here n, small n, is the number of moles of solute, capital N is number of moles of solvent. Ideal solutions. This is the case for ideal solutions we were discussing. What are the ideal solutions? Solutions that obey Raoult's law over the entire range of concentration, known as ideal solution. So ideal solutions obey Raoult's law. There are another 2 points. Delta H, mean change in enthalpy of mixing, will be 0 for Raoult's law, these ideal solutions, and change in volume of mixing will be 0 again. In ideal solutions case, interaction between solute and solvents either 0 or no interactions, or they are similar to the pure solute and solvent. Delta H is no change in enthalpy of mixing. Another is delta V. Now let's discuss non-ideal case. They are opposite to the ideal solutions. When we add a solute to solvent, vapor pressure in such a case either will be higher or lower than the ideal solution or Raoult's law. In other words, non-ideal solutions do not obey Raoult's law. This is because of interaction between solute and solvent are not similar to the pure solute and or pure solvent, and in this case delta V mixing, delta H mixing are not 0, they are non-zero quantities. Now, if vapor pressure of solution is higher than the sum of the pure solvent and solute, they are said to have exhibited positive deviation. They are positive deviation in non-ideal solutions. The reason for such behavior is interaction between solute and solvent is less than pure solvent or pure solute. Pa our pure solute, Pb our pure solvent. This is a vapor pressure of pure solvent, vapor pressure of pure solute. Here is the Xa is a mole fraction, 1 for pure solute. Xb is 1, which means it's 100% present, pure solvent. As we move from here, or let's say here, where solvent is 100%, solvent concentration will keep on reducing and solute concentration will keep on increasing in mole fraction terms. So here, this is ideal solutions line. This black line, straight line, is the ideal solution. But in positive deviation, we see, you see here, it is solvent vapor pressure, and solvent goes higher than pure solvent vapor pressure, then certainly it's keep on increasing, reducing. At certain extent it comes lower than pure solvent, but still higher than pure solute. And remind it here, on this point the solute concentration is significantly higher, so its behavior will be dominating. That's why as we approach the solute, at all the times its vapor pressure will be higher than solute till it converges to pure solute. These are the individual behaviors. These are the, we can say, their total. This is the total vapor pressure. This is individual component solvent and solute vapor pressure at any point or at any mole fraction. At here, this much vapor pressure is contributed by solvent, and this much against it by solute. Delta H of mixing in the such case will be greater than 0. Similarly, delta V of mixing will be greater than 0. There will be expansion in volume. Example is a mixture of ethanol with acetone. They are example of a positive deviation non-ideal solution. Now, next example is negative deviation. That's what we saw. That's all the total vapor pressure variation. Now, if the vapor pressure of solution is lower than sum of pure solvent and pure solute, they are said to have exhibited negative deviation. Negative deviation is due to interaction between solute and solvent higher than pure solute or pure solvent. Let's have a look at a diagrammatic. Here we see the total vapor pressure at any point of time is less than the summation of pure solvent or solute. For example, this is a pure solute. At this point, this is that ideal vapor pressure of solute, but it is lower here. It's the ideal vapor pressure of solvent, but it's lower here. And at this point, this ideal vapor pressure of total solution, but it's lower than ideal vapor pressure of solution. Even in that case, delta H mixing is less than 0, delta V mixing less than 0. As we know, it's opposite to positive deviation. Phenol and aniline mixtures are the examples. That's what we saw. This is ideal, but our solution will behave always low than total components summation.